Our next speaker is coming from the University of California, San Diego, the mass spectrometry query language, a flexible way to discover, explore, and extract mass spectrometry data.
Okay, thank you all for joining me today, and what a wonderful session. I'm having a great time. And so this is mostly a story about my own laziness, so hopefully that rubs off on you all as well. So just to get started, so give you a little background, I'm a bioinformatician working with a bunch of chemists. And so I want to tell you a little story. I'm just sitting at my desk in San Diego, and I'm working in Peter Dorostein's lab, and he comes in, and he has the audacity to ask me a question. And he asks, what if, can we go into all public data that we have available in metabolomics, small molecule space, and can we find all brominated compounds? And then the next week he asks, can we find all siderophores? And then he goes on and asks me all these questions. You know, we're very good friends, but I can't address all of these. This is beyond my understanding of chemistry, number one, and just being able to ask these generic questions and answer them very quickly about where these kinds of molecules might occur, that's a pretty daunting challenge. And so one of the things that after working with Peter, I came to ask myself is, can I develop a universal computational solution to empower chemists to answer this question themselves? So then I can be left alone to do my own thing. So hopefully the answer is yes, or at least we're making progress on the way there. And so one of the things I want to introduce to you all is that we've been developing is called the mass spectrometry query language, or MassQL. And so the high level goals and pillars that support this particular approach are, number one, it's understandable. It's a new language. We want you to some extent speak it to the computer and hopefully communicate amongst other scientists using it. And so it needs to be easy to read and easy to write. Next is that it needs to be flexible. So you need to be able to describe complex patterns that you want to find in mass spectrometry data and use all the information available, so including MS adjacent properties. And it needs to be scalable. Who cares if you can do it on one spectrum? You already have that spectrum. The whole point is to be able to look at one entire file or an entire repository of hundreds of thousands of files, so anything in between. And finally, we want this to be reusable. You have so much domain knowledge in your heads that I don't have, but I would love to have some access to it. So whenever you can write down whatever you're looking for that has some connection to the chemistry and biology, that hopefully can be shared with others truly as a form of communication, so a language. And so let's start with each of these pillars. So first, I want to talk about how it's understandable. And so I'm going to walk you through a little bit of the very first query, the most basic query, looking at tandem MSMS data. So just starting off, if those of you familiar with the structured query language for databases, it'll feel vaguely familiar. But what we have here is actually we can translate these queries that are written in MassQL back to natural languages such as English, and we have other languages, and we'll just put on here Portuguese. So apologies to the native Portuguese speakers on the horrible translation. But here we're just saying, let's look for MS2 data. And now let's put some conditions that you can prescribe yourself. So first row is, let's look for an MS2 product ion of 468 m/Z. And so we can translate that back to English and gives you some connection of what it means. And then what if we want to make it more complex? We can start adding more conditions. So I want to look for MS2 spectra that have 468 m/Z and 660. And so you can see there's just these conjunctions that you can add, like and you can make it more and more complex. And then we won't go through all the intricacies of the language, but I just want to show you the concept to start off with. And similarly, we can translate it back to English, but we can also start visualizing what you're looking for in a more mass spec friendly way and what we're more familiar with. And so not only can we visualize it, but we can also overlay real data on top of this. So you have an MSMS spectrum you can overlay on top of this. And so it can explain to you in a visual sense why the query language found this particular MSMS spectrum and kind of locate you and show you where it is. And so this actually becomes important in other complex situations, but just want to introduce this concept. And so moving on, I want to talk about flexibility. how can we flexibly describe different kinds of patterns? And so the most basic one, as I highlighted a little bit earlier, is the ability to start specifying MS2 fragments. So here in this particular example, working with Daniel Petrus is actually sitting in the back over there. There are particular peaks in the MSMS spectrum that help us identify this particular family of natural product compounds. And so they happen to be this 460 and 660. So you can specify any set of MS2 peaks, and you can specify tolerances. I don't outline it here, minimum intensity and things like that. You can also specify neutral losses and internal fragments as well. And so that's MSMS. And we can also move back into the MS1 space. And so working with Allegra Aaron at UCSD, she really cared about iron-bound siderophores. And so specifically with iron-bound siderophores, I am told there are very distinctive MS1 patterns. And so kind of succinctly described here. And so one of the things you can start doing is writing queries across the MS1 that looks for these distinctive isotopic patterns. And so I won't get into the specific details of it, but it enables that. And then further, now we talked about MS1 and MS2, we are able to combine queries across MS1 and MS2. If you have a particular isotopic pattern in MS1 that you're looking for that you want to define, and some product ions in the MS2 that you want to define, you can put those together in a flexible and hopefully easy to write way. And then also we can start thinking about is if you have retention time. So these MS adjacent measurements. So you can start specifying limits on the retention time. Further, if you have ion mobility, you can start specifying that as well. So if you have one of these instruments. And so actually a lot of the ion mobility work is with Gordon Liu. He's somewhere over here helping us work that out in the data conversions. And okay, did we skip? Okay, we might have skipped a few slides. We will go with it. So is there a way to go back? Oh, the wheel. No, okay. Oh, I got it. I know how to use the computers. Okay, so so I think we missed a few slides in here, but one of the things I want to talk about is scalability. And from the scalability aspect, I mentioned we want to scale up to billions of spectra and hundreds of thousands, at least right now, data sets. And so one of the applications that we worked with is with Nina Zhao, and she's from the University of Washington, and she specifically cares about these organophosphate esters. And these are present in flame retardants. There's hundreds of different analogs of them, and they make it out into the environment. So it's a pollution kind of question. And so what she told me is, even though there's tons of diversity in organophosphate esters, one of the distinctive fragmentation peaks for identifying this particular class of compounds is a 98.98 m/z in the MSMS. So armed with this information, we wrote a simple query looking for that particular diagnostic peak, and it has to be quite large in the spectrum. And so we wrote this query, and what we were able to do is go and search all public data. And so this happens to be 1 billion-ish MSMS spectra from GMPS, Metabolomic Workbench, and metabolites, so as much public metabolomics data as we could find. And 1 billion is a lot to look through manually. And so we were able to get it down to about 338,000 putative matches to that particular query, which is a great start, a couple orders of magnitude is nothing to scoff at. But that's still quite a bit to kind of go through. And so what we were able to do is combine it with a bunch of tools that we actually have at GMPS that are community tools to even chisel this down further. And so one of the first things we can do is start clustering identical spectra together. So we can reduce that redundancy when we see the same MSMS spectrum. And so using a tool called Falcon, developed by Wout, we were able to reduce 330,000 down to 2,700. So another few orders of magnitude. Still, this is quite a bit to look through. And then the final technique that allowed us to really start visualizing and discovering, exploring this particular space is using a technique called molecular networking. And so this particular approach is to group up similar molecules together based upon their similar fragmentation. And so again, we ended up with 169 families of related compounds in this particular approach. And so one of the examples that Nina actually was able to quickly sort through, and this is an example of one of the molecular networks, is, and what she found here were new organophosphate esters from this particular analysis relatively quickly. And so what was unique to, and what was interesting to me specifically is because we cast a large net and you did on the whole repository, and she was able to find new things, which is cool. But she was also able to find new molecules in her own data that she had already published on and analyzed previously. And so it was just very curious to me that using this MassQL tool, the tool itself looked in areas that she manually did not. So I thought that was kind of interesting, and hopefully it was helpful. And the final thing I want to talk about is reusability. So kind of broad reusability of the queries and talking about the ecosystem in general. And so one of the things that we've been pushing on for MassQL, with all languages, is you need to be able to have venues to speak it. And so the way that we've been approaching this is we've been developing software in Python, in R, and it's all open source and free for the community use, as well as integrating this into already accepted community tools. And so one of the big pushes is integrating an MZ-Mine3 that'll be coming out, I think, sometime next year. And actually, Michael Marty is a popular guy, so we also worked with him, and he is integrating it into Unideck. And we also have put it together as high throughput workflows at GMPS that you can try out today. And so one of the ideas here is that there's multiple sources that you can get queries from. It can come from your own head. You can write it yourself. You can get it from the community. So some colleagues that you might run into. Hopefully in the future, you'll start reading it in publications. And we also are putting together a compendium of these queries for different kinds of compounds that people are looking for that are interesting. And once you have that query, we want it to be very simple to go from different software platforms, whichever you're already using, and simply copy and paste it and then apply it directly to your data to help filter, to help extract, and hopefully prioritize what your attention's, where your attention goes. And so, I think this is a great start, but we've definitely got a long way to go. There's a lot of really great mass spec software out there. And so kind of full circle from the story that I was telling at the very beginning, where Peter came to me and asked about different kinds of molecules every week. And so, once I created MassQL, I pushed back on him and said, well, we made this. You do it. And so one particular thing that came up over the last week within the lab Slack channels is certain types of carnitines, or in general looking for carnitine-like molecules, which ionize very well in mass spectrometry, are seen everywhere. And they wanted to ask that question. And so I made them write their own query. And so here's one particular example. Some of you might recognize these particular fragment masses and neutral losses. And then simply they can go to GMPS, they paste that particular query in, apply it across all public data. And we found actually quite a bit. So it's around 2.6 million MSMS, 50,000 unique spectra, and 6,000 molecular families. So they got some mining to do. But again, at least it's better than 1 billion spectra. So in take-home messages here about MassQL, what we hope for it to achieve, and to some extent it is already being achieved, is that it empowers chemists who are generally not, it's definitely people becoming more proficient at software development and coding, but you don't have to be a software engineer in order to ask these kinds of questions at scale. Imagine searching terabytes and terabytes of data that don't even fit on your computer and doing that in a reasonable amount of time once you just learned coding in the last year. That's a kind of tall order. So we hope that it empowers the whole community to ask these kinds of questions. And also we hope, because we've opened up the software and tried to give it out, we hope that other bioinformaticians that develop software, they can add MassQL to add flexibility to their own tools. So that's kind of another venue. And then building upon all of this, we hope that because we can get MassQL out to the community, integrate into tools, it really becomes universal. So you can write a query once for your own data, and you can give it to a friend, and they can apply it on theirs in any software platform that they're running. So it's a dream. We're not there yet, but hopefully we're on the right path. And so I definitely want to thank everybody that was involved in kind of testing and helping shaped some of the ideas. Definitely Allegra and Nina in the Dorstein lab. My former PhD advisor, Nuno Bandeira at UCSD, Neha Garg at Georgia Tech, Alan Jarmusch at the NIH, Daniel Petrus now at Tübingen, and Laura Sanchez and Gordon Liu at UCSC. And if you want to learn a little bit more about looking for siderophores at repository scales, Allegra actually has a poster in the virtual session. So definitely check that out. And thank you all for your attention, and let's take your questions.
Thank you. We definitely have a few minutes. So any questions from the floor? Yeah, right here.
I mean, great work. I really like it. So it looks like, what's returned by this language is the set of spectra, right?
Mm-hmm.
And have you thought about, just returning set of chromatograms instead of spectra?
So broadly, so this is a very small subset of the language. There basically is a way to do that. You can specify saying, I want all M over Z in the MS1 space of say 500, and then you can sum up the entire spectrum, and then it'll just basically give you a chromatogram.
Right. So then you have information, meta information, whether some of the spectra from the same file or like different files.
Exactly. Right. So you'll know which files they came from.
Right.
So you can do this on a lot of files. I'm not sure that it's a succinct way to express it, but in terms of performance, kind of dedicated extracted ion chromatogram tools and things like that might be a bit faster, but it is definitely possible within the language.
Great, thank you.
Great talk, thank you very much. I was wondering how your backend storage needs to look like in order for those queries to be reasonably fast at repository scale.
Reasonable is in the eye of the beholder. So I will tell you how it is in V1 and what we envision in V2. So V1 right now in the repository side, everything's stored as original MZML files. And so when we talk about a query taking a reasonable amount of time, infinity was our baseline. And so these days, doing all of repositories takes a few hours. So, and in kind of V2, we're trying to, have customized data structures. Honestly, reading MZML files, that's honestly the slowest part. So even just getting it out into some binary format that we can ingress quickly will move the needle quite significantly, but there is space for custom data structures and kind of these big data, columnar data formats that I think will accelerate it significantly.
Other questions?
Yeah, great talk, thank you. So my question is actually, the public database came from all the labs depository, right? So there is a tolerance, locally instrument has a tolerance, retention time, mass, IMO, all have tolerance. So is there any way to actually, you can make that increase the filter stringency, actually can some kind of use AI to learn those tolerance for each data set, and then you can actually reduce the actually haystack in the end, the needle in a smaller haystack?
No, that's a great question. That's a great question. So we've taken some steps in that direction, and so there's a lot of people trying to infer mass accuracy directly from the data. We haven't integrated it specifically here. We wanted to be very explicit, but definitely that's something we want to look for in the future, especially at repository scales. When you're looking at your own data, you probably know it. You've done some calibration, but the heterogeneity at repository scales is definitely something we're looking at. We just haven't addressed it yet. But if you want to work together, let us know.
Maybe one more quick one.
Yeah, it's a nice talk. I have two questions actually.
Can you step a little closer?
I have two questions. The first one is, can you make it go to the previous slide a little bit?
Yes.
And another one, one more step. So for example, in this red example here, can I have the queries M over Z range like larger than 100 and smaller than 110?
Oh, the range, like a range.
Yes.
Yeah. So there is not a particular range in the language right now, but there is an arbitrary tolerance that you can put in. So if you put some value, you set, say, 50 Dalton tolerance, then that should give you what are you looking for. And depending on what you're actually looking for, we have this idea of variables. So, and we kind of see it in the Sidera, for example. So you might look for patterns. Imagine two peaks that are differing by 16 Daltons, but you have no idea what the mass of the first peak is. And so you can say the mass of the first peak is X, the mass of the second peak is X plus 16. Let's look for that particular pattern and float it around. And so that's maybe it's what you're actually looking for.
So thank you. My second question is that I guess you already know there's a SQL language in the database area, which can be used in various of database, including the Microsoft SQL, MySQL, something like that. So my question is like, what is the advantage of your language compared to the SQL language?
Yeah, so it's an ergonomics question, and that's the question with all languages, right? So as you can if for those of you who do programming too, it's like, why would you use Python over C++? And it's about who's your audience. And so in terms of what you can compute on, obviously no advantages. You can they can all express the same kind of things, but how you as a community and you as a person will want to express it, and whether you will use it at all, and whether I personally will even use it, that's the big question. So one of the things that when we decided to create this and how to construct the terms, we wanted it to be natural for mass spectrometrists. SQL is great and flexible for databases, but it's not particularly great vocabulary for mass spectrometry specifically.
Very good. Let's thank the speaker.